Okay, welcome everybody to our second day of our first Applied Python programming workshop. We say thank you again to our instructor, Dr. Patrignani, and we hope you enjoy this second session where we are going um, to get some image processing, if I'm right. So with being that said, we'll give the command to Dr. Patrignani.
Okay. Thank you, Adrian. Thanks everyone for joining for another day of Python. I was just pushing the last update to the GitHub repository. And so, yeah, the idea is, well, hopefully now you know some of the basics on how to use pandas, the pandas module to load some tabular data, how to get started with filtering data, how to replace missing values, how to generate some basic plots. And then today we are going to step it up a notch, and we are going to first finish with the material for day one. That is about implementing, the thermal units that we computed into a crop model. And I will try to keep that short so that we can jump on into the topic for day two, which is image analysis. I want to show you how to compute green canopy cover from downward facing images. I know that several of you are collecting images in the field. And so that's something that sometimes is useful. And if you use applications, sometimes you have to do one image at a time. So we are going to learn the basics of image processing and how Python represents images. And then I'm going to show you how to process a batch of images. So in case you have 100 images in your local drive, then you can process all of them. And then so that's the plan for today. Before I go too far and before I dive into the Jupyter Lab for day one again, go to the GitHub repository for the workshop. The link is in the chat. And then you can either download everything again, or if you want, just go to day two and you can try to download at least the images. There are 4 images here, so you can just click in one of these images and then you can click the download button. I think it's easier if you just download everything again. But we are going to be using these images for some image analysis today. Okay, so sometimes when the image size is lower, I think GitHub allows you to see it in a different way, and you can actually read it with the URL. But in this case, it doesn't work. So I'm not sure if there is a limit of about 1 megabyte not allowing to do that. Anyway, just go ahead and download that, and you have a few minutes while we go over the material that was left from day one. Okay. So I want to make a few comments. One of them, let me actually just open the chat quickly. Okay. So one of the comments is that there was a mistake, at least in the material that I shared, not in the one that we did together. That actually we did it good, despite all the mistakes that I made, probably being tired. We did it right, and I found that there was a mistake in the material that I shared with you for those that were not coding. So I forgot to divide by 2 here when we computed the average temperature. So that is why it was giving, I think, 3,000 thermal units or so, when it should be lower than that. Okay, so we did it right in the live demonstration, but I didn't do it right on the material that I shared in advance. Okay, I will not code everything because you have this material, and I think it will be good to save some time for the image analysis component. But I want to show you, now that we have these thermal units, what can we do with it, right? So how can we use this? And one of the applications is to implement or to use some crop model and taking advantage of these thermal units during the growing season. So here's where we finished with this chart, and we computed the amount of thermal units, which was about 1,600. Okay, and that changes with the growing season. So earlier planting days or longer growing seasons, or warmer years, will end up in larger thermal units. Different base temperatures or cardinal temperatures will also affect the cumulative number of thermal units. And so that's why it's so hard sometimes to compare with other people, using different sort of cardinal temperatures. But anyway, we got it. So we have that for every day. I think it was 231, 32 days in the growing season. So now we can take advantage of this. And there is a very simple model that was developed in France in the early 1980s. Let me show you here in the references. Is a model by Barrett, 1986. I don't know any French, but you feel free to search for that.
Dr. Patrignani, I don't think we're seeing the right screen.
Oh, okay. Good call. Let me just, is that better?
Yes.
Okay, I apologize. Yeah, feel free to interrupt me because, okay. So let me show you again. Here is where where I made a mistake. So we need to make sure that we have that divided by 2. And I just updated the repository, so the latest version should be there. And here's where we finished. Here is the thermal units. And now we can actually implement that into a crop model. And as I said in the references, here's where we are. This is the model. And he also is describing in very great level of detail in this book by Daniel Wallach. Okay, the model is very simple. Leaf area index is modeled as a function of the thermal units and some, thresholds for which, the crop starts to decay or to senesce, and as a function of the maximum leaf area index. So, there is no water stress, there is no nutritional stress, it's everything based on the incident radiation. And then we are converting that leaf area index into an estimate of biomass. And we had to do that for every single day. And so basically, there are some assimilation efficiencies, and here you have the details, right? So we use that photosynthetically active radiation, which is about half of the solar radiation that we receive on a daily basis. And that is what is driving the model. So photosynthetically active radiation and thermal units. And of course, here there are some, the intercepted radiation use efficiency. We have, the efficiency of the plant on using that radiation in the, in the tissue. And anyway, I don't want to dive into the physiology, but we also have coefficients of extinction for those that are familiar with it. That is basically tells you how is the light going into the canopy. And that's basically all. There are very few parameters. So T1 and T2 control the timing of the leaf area index dynamic of the growth. So the T1 will be the inflection point at which it reaches the maximum slope, so the maximum rate of growth, and then you have T2, which is that dictates the senescence part of the model. Again, very simple. It's just for potential grain yield. It was described or proposed for winter wheat, but I'm pretty sure you can adapt other models to this. Other crops to this model. So here are some of the parameters that I defined. I assume a maximum leaf area index for winter wheat of about 7. That's what we usually see in the field for intensive management, well water crops. A radiation use efficiency of about 1.85. And here you can see that I didn't use, for instance, I didn't use this radiation use efficiency. I didn't use this, and I didn't use another common notation that is probably RUE. And the reason was I wanted to stay as close as possible to the notation on the book or on that model when it was first proposed. So sometimes we deviate from the, from this suggested Python syntax just to stay closer to the model that we are following. So then if we have to refer back to that, to the model, we know exactly where to find the equations. If someone else is reading or following the same model and the code, they can match the equations. Sometimes it's nice to even place here, for instance, when we describe the equations, we can say equation in page, 34 or something like that. So you know exactly. So you can say equation 3 in page 34 or something like that, right? So really nice to document that. And remember, when you're the only one coding is one thing, it still helps you to document, but the issue becomes when someone else is reading this, whether it's your advisor to look at your code and to your logical thinking. And I use code a lot for advising. I can really see what students are thinking and how they are thinking logically. And usually there are problems that are in the logical arrangement of ideas or processes. So coding allows me, it's like I have X-rays, right? And I can actually help much, much better than if you had to describe to me what the problem is. Here I can really see it in action. Okay, and the last one, there is a harvest index that is going to convert these biomass or above ground biomass into yield. So let me just be clear, this B here in the model is above ground biomass today that is simulated based on the above ground yesterday. So we can run this. And that's just defining the parameters. So I want to have that separate from the implementation of the model. Here we have this equation right here is the same equation that we have here. Is the first equation for a leaf area index. It's this one right here. Okay? And see how I didn't hard code anything. So I didn't come here and I did this. I didn't do 7 there. I placed the leaf area index maximum. So if I actually want to change that for another crop or for a different scenario, I can come here, change my settings or my parameters in a different cell and rerun the code. And I don't have to worry about changing values or variables in every single instance that I use it. And here we have the other equation that is the above ground biomass. So note that here we have the letter T minus 1 and T, which implies that we are going to calculate that for every day. But in Python, we can do that all in one go right here because we already had the cumulative thermal units. And so these 900 thermal units is where the crop will have that highest rate of growth. And then there is another exponential term that is for the part after maybe antithesis or so when the crop starts to senesce. And of course, because it doesn't know that it needs to stop in 0, it will keep, this part will keep driving the leaf area index to negative values. We need to bound it and make sure that the leaf area index, it becomes negative, then to be 0. Okay, so once we compute the leaf area index, then we pass it right here. So it's leaf area index is there, and we pass it right here. And we pass it into the above ground. And this part, in case you're interested, so 1 minus e to the minus k times LA, that part, that is actually the intercepted solar radiation. And that is why it's multiplied times this. So this is equivalent, let's say, to canopy cover, to the fraction of canopy cover. And that is why many people are, instead of measuring leaf area index, they are actually using green canopy cover as a proxy, because this term is actually that area of the crop that is intercepting solar radiation times the solar radiation, or the photosynthetically active radiation, times some efficiencies and times the radiation use efficiency. Okay, so that's what's going on there. So if you want to make a model simple, that's why I really like canopy cover. You can actually do this. If you had a canopy cover, you can just do that. They will not be exactly the same, but they are fairly close, at least for wheat. There you go. And I don't know if I forgot to explain anything else, but so once we have the model, I forgot explaining how I got the photosynthetically active radiation. That is here. So in the Ashland Bottoms data set, we also have the solar radiation, the daily solar radiation. And I assume that about 50%, 0.48 is the photosynthetically active radiation, that the spectrum of entire solar radiation that we get on a daily basis, the part that the plants can use, is about half. So that's how I estimate it. So basically, we are using minimum earth temperature, maximum earth temperature, and daily solar radiation for the entire example. And all was obtained for the Kansas measurement. Okay, and once we figure that out, basically these 2 equations right here and right here are these 2 equations. Okay, so it's basically following. You can see that if you look at this syntax or the LaTeX syntax, is very close to what we actually write in code. So that's actually really nice. And that's all. Really, that's all. It's once we run it. Here with the integer location, and -1 is for accessing the last value, and that's how I get the last, the last amount of above ground biomass, which is this value. So we don't have to sum it again because we are already working with the cumulative biomass. We just retrieve that last value of the column. And then we need to do a little bit of conversion to express grams per square meter into kilograms per hectare. And this is the potential yield that that particularly wheat crop will have, which I believe, I don't know if there is any wheat experts in the room, but this is about right. Usually 6, 7, maybe 8,000 kilograms or 8 megagrams per hectare is something that we can achieve in this region. And then I just created some plots, and you can actually see that it does make some sense. We have very slow growth at the beginning, almost no growth during the winter time. And then we have this massive growth rate, which is actually what we are right now. All right. If you went to the field maybe 2 or 3 weeks ago and you go today, you will see the wheat is completely different. Probably what had a 40–50% canopy cover, and now you will go and it's fully covering the ground. And then that will be for leaf area index, and this will be for the cumulative biomass. And if we change some of the parameters, so let's actually do one. So instead of 900, see, it doesn't decay all the way. So that means that maybe we need to have a little different parameters. So we can actually use maybe 700 for that T1 parameter. And let's see if that actually, there you go. Okay, so this is we move this transition that I was talking about a little earlier in the season, which actually makes sense. This is so early March, and that is usually late February, early March is when the wheat starts to grow quite fast. So now you see the model in action, and it's very easy to change parameters and rerun it again. And one more time, it's all thanks to this modular, layout of the Jupyter Lab. Okay, well, I just wanted to finish it up because it was probably good to cover how we use those thermal units. Maybe you're using the thermal units for something else, but I think this is a great example that is fairly simple. So I'm going to switch now to image analysis. Okay, so we're going to switch to image analysis. I'm going to go to day 2 right here. And now I'm going to open. So hopefully you have these. And there should be a notebook with the example in case you're not coding today. There is an HTML version that you can actually see everything in as a website. And this is another thing here that I need to probably show you. Let me just go back to the day 1 and show you one thing. So you can have all of this, and you can actually come to File, Export Notebook As, and then you can choose all these different formats from PDF to even some sort of interactive slides in JavaScript, and then HTML, LaTeX. So anyway, tons of possibilities. Since we are here also, I want to show you that I added a few things. So let's go to the very end. There is a Q&A section where I added the questions of many of you and my answer, and some of the students' answer that also contributed into the chat. So some people couldn't get the results on the screen. That could be due to different things. Either maybe just make sure they run the cell, so the cells do not run automatically as you type. Make sure your cell is not a markdown cell. And also, if nothing is displayed, maybe that's just because it's the way it is. And so you may want to force that using the print command, for instance, just to see what is the content of that variable. People are wondering about DPI for the bokeh plots. Bokeh does not use or does not allow to set in the DPI. That's usually related to the size of the figure. So with this library, You just, if you want a higher DPI, just set a higher plot size. And I place some of the code next to one of the right here. What is the first chart? Right here on how to export. But at this point, the best way is just to click the save button here, and that will be easier. But if you want, you can actually export this in a different size on the one that you plotted. So you can keep it, fairly small for displaying purposes in the Jupyter Lab, but you can actually go and specify larger plot dimensions for saving the plot. And then what else? So, if you're using Matplotlib, or, that's one of the most popular libraries, and this is the one we are going to be using for image analysis, then you can actually use this code where you can actually specify the DPIs, and that was provided by another student. I think it was Sarah. And then, as people asking about table of contents, I did not. Well, there is a way of finding a floating table of contents. You can install an extension, and if you go to this little icon right here to your left, if you click there, you will find that you can install extensions. So there are all sorts of extensions for different, functionality. So there's just a ton. So this is one of the really nice features of the Jupyter Lab ecosystem, that you can add, you can even add, ways of highlighting text when you make a comment and all this kind of stuff. But there is a way that dependencies and everything that happens, we are coding now in the browser. So everything that is interactive or dynamic usually happens in a different language, which is called JavaScript. And that's what drives much of the dynamic aspects of websites. So that means that you had to install other things that drive that in the background. And so I didn't really want to create a ton of dependencies in my computer, but I did find that you can make a table of contents like this. So if we're going to go, let's say, for loading tabular data, you just click there and it will take you. That's kind of interesting. If you're doing a tutorial, then people can just follow along. So how I did this, if you double click here, you can see that this is sort of a link. So this is the title that I want to appear in the link. And this is the connection to that particular cell. So you had to use this kind of notation. So let me show you. Let's choose this one for the exercise description, the first one right here. So you double click. Here there is an anchor. Yeah? And this is not Markdown. In fact, Markdown is a markup language, but there is something called HTML, which is also what makes up most of the websites. And Markdown is a simplified syntax that actually it gets converted into that HTML. So it has some limited capabilities, and sometimes when we want to go a little further, we need to go and use pure HTML. Okay? So in fact, if you do right-click, no, it's not going to work now. But if you go to any browser, let me see if I can open this. You go to any browser and you click inspect, and you go to elements, you can see here there are all the elements of the website. So this is HTML, and then much of the functionality is given by JavaScript. So maybe not necessary, but once you feel a little more confident with coding, you can start adding these little things or code snippets that will make your code a little more complete. And everything is hidden once you run it. And I don't know if there was any other one. And then someone asked for the piping operator. Python doesn't have a piping operator, but because this one actually represents OR, the bitwise OR statement. But what we can do in Python, as I showed you earlier, is we can chain different commands or different methods. Like let me show you an example. Like here, so you can even do, let's say, round here, for instance, to 2 digits, right? So you can keep chaining methods, and the result of one will go as an input to the next one. So these are methods of the objects, and some other languages they're different. So each language has its own paradigm and specific syntax on how things are done. Okay. Any questions about the tutorial for day one? We already spent about 30 minutes, or but I'm willing to answer maybe a few questions if you have. Okay, let's jump into day two then. Close that. And I'm going to create another live demo here. So rename. Okay. So we're gonna do image analysis with Python. We're gonna convert this into a Markdown. And we are going to be using few libraries only. And then one thing that I want you to have is to make sure that your pictures or the images and your Jupyter Lab are in the same directory. That will make things a little easier. Yeah. So the first thing we had to do is to import modules. So for this one, we are going to import NumPy as NP, that's the alias, so that we don't have to type NumPy all the time. And then we are also going to import perhaps the most popular library in Python, which is matplotlib. And then there is a specific submodule that we are going to use called pyplot. And because all of that is very long and we don't want to type that all the time, we are going to, again, assign this module an alias. It's going to be as PLT. Okay? So this will help us to plot, and I will add a few more changes here, but this is the classic way, or the plots will look with the classic theme, basically, in Python. And then there are other themes that we can add to the plots, like the ggplot theme or the Seaborn theme. And, we are going to try some of those because they look a little more stylish, more, more modern. But let's start working. Before we load any image, before we do any operation on an image, we need to understand how images are represented in the computer. And for that, I think it will be great to learn a little bit about matrices or so 1, 2, and 3-dimensional arrays in NumPy. And sometimes we can see what is a 1-dimensional array, a 2-dimensional array, but it gets a little harder once we start thinking in higher dimensions. So let's see if we can do some basic NumPy operations here. So I'm going to assign just A, B, and C for 1, 2, and 3 dimensions. So A, this will be a 1-dimensional array. Okay. And now we are going to use NumPy, and we are going to just create an array. And we are just going to place 1, 2, and 3, perhaps. And that's all. Then we have A, and that's what we have it. Okay, it has only 1 dimension. It's just a row. If we do shape, then we can find that it's a 3 by nothing because there is no second dimension. Okay, so if you're in other languages, to say I work a lot with MATLAB, and here in MATLAB it would say 3. It would say 1 by 3 or 3 by 1, depending on the orientation. So some other languages do specify sometimes a second dimension, even though it's just a single dimension. Okay, so we can actually also do. Let me use the print so that we can keep track. If you don't use the print, it will only display the last command. So we are going to do print. And in this one, I will do type of A. And you can see that it's a NumPy is an ND array, which stands for n-dimensional array. That means that in NumPy, we cannot create only 1, 2, or 3-dimensional arrays. We can create even larger, n-dimensional arrays. Of course, sometimes they are hard to visualize, but let's see if I can show you some examples. Okay, so that's a 1-dimensional array. Now let's do a 2-dimensional array. And now we are going to create B equals NumPy array. And then here we need to pass, we need to define the array. And here I'm going to do a few things. So we can do 1, 2, and 3, and then we can create 4, 5, and 6. But that will not work. So we need to wrap everything into square brackets like that. So that means we got 2 square brackets. Okay, and we need to place a comma right here in the middle. Okay, so let's do that. And now we do print B shape. And now we get that is a 2 by 3. So 2 rows and 3 columns. There is another property, it's not shape, but it's called size. And that gives you the total number of elements. So that will be 6. Yeah. And these are properties. These are not methods. These are just properties of the object. Okay. And this is also an ND array. So we can actually move to a 3-dimensional array. And now it gets a little more complicated to create. So I'm going to show you also another functionality of NumPy. So we can actually create arrays of, with all filled with zeros that when we are going to replace as in our operations, or all filled with ones, or with pretty much any value that we want as a placeholder before we start some computations. Sometimes when we run a very extensive and memory intensive operations, sometimes we want to pre-allocate the arrays in memory so that the computer, before running, let's say, a for loop or something very intensive, already knows how much memory needs to allocate before it starts running. So it doesn't have to do that operation of reallocating a growing array in memory in every single iteration. So this is much more efficient sometimes to pre-allocate the arrays. Of course, that is if we know the size. Sometimes we don't know the size and there is no other way. Okay, so we are going to use the NP zeros. And here I'm going to create, let's say, 5 rows and 5 columns and 3 layers, or 3 pages. So let's see if we can do the print. Oops, sorry. 3, so C shape here. What did I do now? NP zeros. Oh, I think I need to wrap this to pass the dimensions. There you go. Okay. Okay, so that will be a 5 by 5 by 3. And here you can think of the pages of a book. So we have 5 lines, and then we have 5 columns, from the spine of the book towards the edge. And then we have 3 pages. Yeah, that's more or less what this means. So if you have a book of 50 lines, and I don't know, each character is a line in a column. I don't know, we have maybe 150 of them. And then we have a 300 pages, then you have something like that, right? And you can even call the size, and then you can get all the values that you have. And the reason this is important is because actually this is how we represent images. So let me go back. So this could be an image that it has 50 rows and 100 columns. And then it has 3, well, let's just not make it 300. There you go, 3. And it has 3 bands, the red, the green, and the blue. You may have another picture, maybe a remote sensing image that maybe has more bands. Let's say something from MODIS, the NASA satellite, maybe has 10 or 12 bands or something like that. Then you will get something like this. Okay, so each band or each page of that book represents a band. So if you understand these, then dealing with images will not be that difficult. But this is at least how Python and some other languages represent images. There are other ways of representing images, but this is perhaps the most common among the different languages. Now let's print this. Let's actually print the B and what it looks like here. Okay, so you see that this is 1. There's a comma, and then there is another array there, and then they are all wrapped by a bracket. So when we go to a 3-dimensional array, things get a little more complicated because now we have this. Right, let me just do the 5 so that you can see. Right, so we get something like that. You can see the level of nesting, and that is really what dimensions here, n dimensions, represent. Things are nested so that we know, we have 5 rows and 5 columns, but really the computer doesn't see that's 5 rows and 5 columns. So it's for the computer is a long string of characters, and so he has to know at what point this is 1 row and this is a different row. Okay, so that we know the very basics on how to, how Python, particularly NumPy, represents arrays. We can move on. And I want to make a really quick comment that doing NP array, let's see, 1 is different than doing just like this. So let's do, actually, this will be ABC, it will be D, and this will be E. Okay, let's do this, and let's do type print type of D, and let's do print type of E. Okay, they are different. One is a NumPy array, and the other one is a regular Python list. And so these ones here do not have some of the special properties of NumPy arrays. So they cannot do element-wise operations. We cannot generate all this kind of stuff. So NumPy, the reason it's so popular is because it allows us to sort of vectorize operations. Very good for vectors and matrices. In fact, I think I mentioned that most of the data science packages rely on NumPy to some extent. Okay. Now we are ready. So now it's time for reading the image. So read an image, time for action. So how do we do this? There are multiple modules, but Matplotlib is very complete. So we can actually use it, and we can actually read an image directly using Matplotlib. So we're gonna do RGB because that's what the image looks like. So RGB, and here we're gonna use PLT, right? We're gonna call that alias that we have here, and we are gonna access a specific method that is imRead. If you're a MATLAB programmer, or you ever use it, you will see that between Matplotlib and NumPy, it's pretty much the same syntax. They are both inspired in MATLAB. So things are very, very similar in terms of notation and function names. Okay, so we have PLT imRead, and now what we need to do is provide the file name. And in this case, I'm gonna use the very first one here. So I'm gonna type soybeans. I'm gonna use the auto completion, and I don't want to make any typo here because there are lots of numbers there. So we are gonna do that, and then we are gonna move on. So this is a case where nothing will display, and it's okay because we never told the computer to plot anything. We just told the computer to read it. So now if we want to see what is inside, we can actually do print RGB shape, and that will tell us the dimension. So this is the number of rows and columns. And we can also do print, and then we can use, if you want to know how many pixels are there, we can find this, and if you divide this by 1,000,000, then you will find that this is a 14, nearly 15 megapixel image. Okay. And it's always really useful, as I mentioned earlier, about plotting your data. Checking, when we were doing displaying the first few rows of the pandas data frame to check our work. The same here. It's always good to check dimensions to make sure that the computer is doing what we intended to do. Okay, so it's easier. It seems to be slower because let's just code it. Let's just solve the problem. But so if we have a type, a bug or something, then sometimes it's really hard to find it, particularly once our code is pretty lengthy. So now we have that. Now let's just plot it because I think we're going to be working with images. That's what we need to do. So we're going to do PLT figure, and I'm not going to assign anything, any particular dimension. I just want to get the picture there. Then we can add or remove a few things that we don't like. So PLT imShow. Here is where we pass that RGB image, and now we do PLT show. And there we have it. Okay, and this is an experiment that we were doing this is an on-farm experiment where we were tracking soybean growth using time-lapse images. And today I'm going to show you a few interesting things that we found, and also how to process. In this case, would be 4, but the solution that I show you will work with any number of images. So this is the original image, but you can see that there are some limitations already. We had the tripod here, so the cross arm that holding the camera wasn't long enough, so we got a little bit of the tripod there. So it will be nice to actually crop this image. Sometimes what we do is, we go to a separate software, and then we crop the image, and then we do all the stuff maybe with Python or R. But that's not good because we are changing the raw data. So this is the image as it comes from the camera. So it will be really nice if we can crop and do all the analysis in Python so that we don't have to first do extra work in a different software. That is also hard to replicate. Imagine someone else trying to click on the same pixel and, and dragging and cropping the same square. That will be pretty hard to do. And the other one is we don't want to change, we want to keep a blueprint of these steps. So I'll show you how to do all these steps now. So now you see this, we can actually do PLT axis, and we can remove the numbers. But sometimes they are handy if we need to look at some dimensions. So I'm going to keep them for at least for this one. Okay, and here you can see the rows and the columns. Okay, so columns are X and rows are Y. And you can see that it matches, at least these two match what we see in the picture. The 3 is the one that is not appearing, and that is because when we see an image like this, all 3 bands, red, green, and blue, they are already showing, the final result, which is the colors that we see. It's the combination of those 3 bands that we see in this case. But we can actually access individual bands, and we can actually plot them. Before doing that, I want to go. Well, let's just keep going like that. I want to show you maybe the difference in another plot. So let's keep moving. So now if we want to crop this, we need to learn how to crop or slice. That's the term that we use for selecting a portion of the NumPy array, slicing. Okay, so slicing, very important operation, slicing, so that we can select what we want from this image. So let's suppose that we want to access the first pixel. We can do RGB, and then we do 0. That's the 0th row, 0th column. And remember that Python is 0 index, which I already showed you in these 2 steps, but it also applies to the band. So band 1 will be the second band. So band 0 will be the first band. So that will be the first pixel of the first band, which is 184. So that will be the red intensity of the first pixel right here. You can also see that the image starts, the row starts from the top and the column starts from the left. So the first pixel will be right here on the top left corner. That's opposite to how you usually represent XY plots, where X and Y starts both from the bottom left corner. So, but what happens if we want all 3 bands, the red, green, and blue for the first pixel? Well, we can just do the colon operator, which means that we are selecting all of them. And all the 3 bands, but just for the first pixel. Okay, so here we have it. 184, which is the one that we obtained first, but now we also get the green and the blue intensity. And this is why, again, NumPy is so powerful. Look at the notation. It's very, very simple. It's super easy to work with matrices and images. It's very, very compact syntax. And so now we can actually select, using this, we can select the specific patch. So let's do that. So we're going to take the slicing to the next level. So select a patch. And here what I'm going to do is call this RGB patch. I'm going to do RGB, and now we need to know what we are going to slice. So the tripod of the leg seems to start around here, about 600 or so. And then we want everything on this side. But I also want to make sure that I keep some sort of square. I don't mind grabbing a little bit of this part, but I want to keep it as square as possible so that, we discard everything on the edges as well. And that's your choice. Maybe you just want to crop, all the image just from this column is about 750 to the right. You can also do that, no problem. I'm just going to crop more or less about the center just to keep it simple. So, we go from 500 to about 1500. So we are going to write that. So that those are the rows that we want, 500, to 1500. Okay. So that's how we say from and to. So from 500 to 1500, those rows, comma, all of that will specify the rows. And now we want to do, let's say from here will be about 1000 right there. So 1000 to, and I'm going to keep it square. So this one is 1000 pixels. So I'm going to keep it here to 2000 pixels. So that will be from here to here like that. Okay, and I want all three bands. So we can even select like that, or we can select like this. Okay, so I want the red, the green, and the blue. So let's see if we can actually create a figure. So PLT figure, oops, and then PLT im show, and we're gonna do RGB patch, and then PLT show. And there we have it. That's the part. Let's see if we do something different. Let's see if we just want a slice here. Let's just select something across the tripod leg so that we know that we are doing the right thing. Because sometimes when we see this, is hard to see exactly. So if you want to test your learning, just choose a trivial example where you know exactly what you need to see. So for instance, we can select from 0 to 17. I'm going to change this. You don't need to code this, but to the, let's say 1750 here to the end, or sort close. And then here we're going to select from, let's say 500 to, I don't know, to 600. So I'm going to do that and see. So now we have that. You can see the tripod leg right there. Maybe I need to be a little more generous with there we go, right? So that's sort of, we are testing our intuition about slicing, and it seems to be working. Yeah, so you can do that as well. Okay, let me reverse this so we can keep working. And sometimes you can, maybe you want to set, instead of going to a specific number that is hard coded, maybe you want to get, the shape of the, this part, and do times, 50% of that, or 25% of that. If you want to, remove only 10% of the area around, you can do all sorts of stuff. Just make sure that when you work, in slicing, that you use integers. So if you divide this by 2 or by 3, and you don't get an integer, then make sure you round that before you pass it into the slicing function. Otherwise, it's not going to know exactly which row it needs to go. Okay, let's go back to our patch. And now is when I'm going to remove the axis, because I already know what we got. So now I'm going to have it like that. Okay, so now the question is, what is the percentage of green canopy cover of this image? And that's what that would be the goal today. Not just this image. We are going to first do this image as an example, so that we learn all the steps, and then we are going to apply that to all these 4 images. Okay. So now we are going to, so now we need, we have several steps. And so the first thing that I want to show you is to convert the bands in the image. So I want to show you how to visualize them. And we can keep using this. I think in the final version of the tutorial, I already converted this to a floating point, but it doesn't matter for plotting purposes. So let's do PLT figure. Seems logical to display separate bands. Display separate bands. Okay. So we are going to create a figure, and now we are going to create multiple figures. And so we are going to use PLT subplot, and we want, let's say, if we want to display the red, the green, the original, the red, the green, and the blue, then we can create, a 2 by 2. So we're going to do a 2 by 2 array or grid, and then the first plot of the first image will appear in the first one, right? So that's what we do. The first 2 numbers establish the size of the grid, and that will be constant across the entire, all the figures. And this one is where we want to place the figure that we are about to define. So we're going to do PLT im show, and here I'm going to do RGB patch, and then that's pretty much all. We can actually give a title, so PLT title, and this will be the original, or let's just call it RGB patch, because the original is the one that we cropped down. So we got that, and now we are going to remove the axis. So off that, and now we need to move into the other one. So I'm going to write this one more time. So we're going to do PLT dot subplot, We're going to do 2 by 2, but now it's the second position. So what image do we want here? So we're going to do PLT in show. And now we can call RGB patch, and we can do this. All the rows and all the columns for the red band, which is 0. Okay, so we can do that. And we can do PLT title. This is called red band. And now we do the same thing. So PLT axis. And many of you may be tempted to copy paste. Sometimes I do it as well, but it's really nice if you type it all, and then it will be even faster sometimes than copy pasting and removing. If you can keep your 10 fingers on the keyboard, you can be really fast. So this would be off. Okay, now we had to do a PLT subplot 2 by 2, and this is the third one, and this one is going to be the green band. And so we are going to have RGB patch, and this is going to be all the rows and all the columns, but for the second layer, right? PLT title, and this is going to be now green band, and now PLT axis off. You can see that you can actually set some different properties for the different figures. So we can have some with the axis, some without, but let's just remove them all. And then the last one will be PLT subplot 2 by 2, and this is the fourth one. And now we are limited, right? Because a 2 by 2 only has four places in the grid. So this will be the last one. So it will be PLT in show, and we are going to do RGB patch. And now we need to do all rows, all columns, and then the last one, which is 2. Title, PLT title, and this will be the blue band. And then, oh, and that's not big. There you go. And now PLT axis off. And now to finish, we are going to make everything a little compact. So we're going to do PLT tight layout. That's a function. And then we are going to do PLT show to display. See, PLT show goes always at the end. And now hopefully we will get something interesting. Okay, so we got all the 4 tiles there as expected, but the colors look a little weird, and that's because the color map by default is, I think it's called Viridis, and maybe it's not the best for at least this application. Also, the size seems a little too small. So we can do a few things here. We can do a figure, so we can do fixed size. And we pass something called this is called it's called a tuple. Things in parentheses sometimes are called tuples, which is different than a list. It's different, something called a dictionary. So this is one of the data structures for storing data in Python. And see here we can do something, we say 14 inches by 10. This is in inches. We can do that. And now we should have something a little larger. Yeah, that's looking better. Now we can have, instead, we can change the color map, let's say to grayscale, and we can come here in show, comma, color map, and we can do gray. Let's just try one of them to see if it works. There you go, it does work. Okay, so we can change all the other ones now. That goes into in show. There you go. And now we can have all of them in gray. So you can see how the different, the different reflection or different reflectance of the bands. We can also change this. Maybe we want to have, instead of gray, we can have reds. And what is this one? Green. So greens. Oops. And maybe blues. That would be different tones of red, green, and blue. I don't know what is the best alternative. It just, you have to choose whatever makes sense for your data set. This one is just colorful, but I'm not sure whether it's useful or not. But anyway, that just gives you an idea. Okay, I think you can also, someone asked about DPI, and I think you can also even set DPI here. So you can maybe set DPI to 300. That's usually for publication quality, but I think it's gonna look very large. Let's see. It's also taking some time. Let's see, hopefully I'm not crashing my computer. Okay, well, it looks a little larger. Maybe I can hide this. And yeah, definitely looks a little larger. But anyway, you can also set the DPI there. And if you want, you can actually, before, if you want to save this, just do PLT here, and then you do save figure, Okay, and then you need to give the name. So let's say mosaic JPEG, and then you just, you can also specify the DPI here, as someone mentioned earlier in the comment yesterday. And so maybe there's no need. So you can actually increase the DPI when you're going to save it without having to increase the DPI when you have it on display in the notebook. And in that case, it might save you, it took quite a bit of time to plot. So, and if we run this now, it should save it. Let's see. So the figure should appear somewhere in here. Let's just hold on, let's refresh here. There you go. You can double click. And see, it's quite large. A 300 dpi image will be fairly large. But anyways, here. And so you can use this to publish your next paper. Okay, so let's keep moving now. We're doing trading time. And there you go. Let me create some, because I always do the same mistake. Okay, so now that we have that, the idea is to compute the green canopy cover, but there is a problem. And the problem is the following. Let's see if I can show you. So let's do RGB patch. We are gonna get the first pixel. Let's just get the first band of this first pixel, and let's do type. I really want you to show this type. And okay, so it says numpy.uint8, and this means that it's an unsigned integer of 8 bits. And this is how the image is represented. Basically, each pixel of each band can have a value that ranges from 0 to 255. That means that there are 256 possibilities. Is an integer, right? So there is no 254.5. There is either 254 or 255. So it's an integer, and unsigned means that it doesn't go negative and positive. It means that all the range is on the positive side. And this is how all the colors are represented, right? So each pixel and each band can have a value between this, and that's how we create all the colors in the RGB color space. There are other color spaces. If you're familiar with the Munsell color chart in cell science, sometimes we use the hue, value, and chroma, and there are a few other color spaces out there. Okay. So we cannot do operations. So we need to convert this into a floating point so that we can keep track of decimals if we want to do some sort of image processing and create different ratios between these bands. And here is where your knowledge, your agronomic knowledge, your knowledge of computer science is where you have to use all of these to filter out, to classify what is the property or the feature of interest. So the computer now cannot help you very much in the sense of you need to know what approach are you going to use or how you're going to do it in order to achieve that goal. Okay? So that sometimes becomes by following examples, by exploring different relationships. It all depends on the ingenuity of every single person. Okay, so what I'm going to show you today is how we develop an application called Canopeo, which is for analyzing green canopy cover from images like this one. And I'm going to show you more or less what I did when we were first creating the application. And so in this case, you will end up having the Python code to process your own images. But the goal is to learn the basics of NumPy arrays, on plotting, on bands. I think that's the goal of this tutorial. And every time that we deal with the images is also fun. So let's keep going. So the first thing that we had to do now is to convert unsigned integer of 8 bits to floating point. Okay? And the reason is we are going to do some ratios or divisions between these layers. And whether you have to do a division or a subtraction, that is again part of the research that you might be doing. And so the first thing we are going to do is define each band separate. So we're going to do R. It's going to be RGB patch, and there's going to be all the rows and all the columns for the first band. And I'm gonna wrap this with NP float. I'm gonna choose float 32 bits. You can also use float 64 bits. And this represents the number basically of decimal places that it will hold. And so the more decimal places you want to have in each operation, the more memory is going to use. So that means that if you're not too concerned about rounding issues, or if 7 decimal places is fine, then maybe you can use this one. Sometimes in long numerical simulations, you need to have greater precision, and because otherwise, some error that accumulates, it can propagate and cause some serious mistakes, in future steps of the simulation. But for this case, float of 32 will be enough, and it's also fairly fast. So we're going to use that one. This is also fairly used sometimes in deep learning or machine learning when computations are very intensive. So float 32. I'm not sure about float 16. Anyway, I'm going to choose that one. Wrap it up there. And now, so we are going to have here the red band, and then we need to do the same thing with the blue band. So we need to copy on this red band. And in this case, is what I'm going to copy that quickly 2 times. This would be green. This will be blue. I'm going to go to the beginning. So red, green, and blue. And then here, don't forget to change the values. Otherwise, all of them were going to be the red band. So this will be 1 and 2. Okay. Now we can check the size. I would say the shape. We tend to say size, but the size in NumPy has a specific definition, which is the total number of pixels. So I'm going to check the shape. And you can see it's 1,000 by 1,000. But see that there is no third dimension now, because we decouple, or we extracted these separate layers or bands into individual layers. So there is no third dimension now. So each of them has the same size, right? 1,000 by 1,000. Okay. So now that we have that, we didn't have any errors or issues. So now it's time to do some operations on these bands. And again, here's where the NumPy arrays and the element-wise operations are super handy, because we don't have to iterate over each row and each column to do a division or subtraction. We just do all of them at the same time. NumPy arrays knows what to do for each pixel. So something that we found in this research is that the red to green ratio was very good at discriminating the green canopy cover from the background. So we are going to use that first. We're going to define this as the red-green ratio. And to do this is just this, R divided by G. And that will do the division for all these. Let's find out what is the size of this. Size of that. Okay. So that's 1,000 by 1,000. That's a million. Okay. So it's going to do all that million operations, those million divisions for each pixel like that. And so very, very neat syntax here. So let's do the, we also found that the blue to green ratio was effective, at least to discriminate sometimes the sky, blue to green ratio. And I'm going to show you now in histograms what, why this is happening, but let's just first compute it. And then we also, we had to adjust a little bit, because sometimes it was selecting pixels that were a little too dark. So we define an excess green just to select pixels that are, that have a high intensity on the green band. And to do that, we define the excess green, which is 2 times the green minus the red minus the blue. Okay, you can see why they call it excess green. So this would be the red to green ratio. This will be the blue to green ratio, and this will be the excess green. And we're going to run this, and we get a warning. It says divided by 0 encounter in true divide RG ratio, and the same happened on the VG ratio. And that's true because we have some values here that are 0. And so if you recall to, high school, something divided by 0, sometimes we cannot do it and the computer will actually throw infinity. So we can actually check that. So b.min, that will show you that in fact our lowest value is 0. We can also check the maximum, for instance, and we get that it's 255, similar to what I just told you here. Okay? You can access that for any other bands. So a warning is something that we should be aware of. The computer is saying something weird happens. You should take a look, but it's not stopping the execution, because maybe we were already aware of this and we are going to handle that in the next step, or maybe we just want to ignore it. But the computer does, this is, sometimes we get these warnings. It's just not good to ignore them and keep going. At least see whether this is a reasonable thing to ignore. So we are going to actually handle this, because if then we may end up with excessively large numbers. So we are going to address this in the next step. So we are going to redefine the RG ratio and the blue to green ratio. So we're going to do RG ratio equals, and in every place that we have, let's actually right here, I want to show you what's saying. So let's see if we can do RG ratio max. What is the maximum value? See, the maximum value that we have is infinity. So this is going to bring some problems, because when we want to plot or we want to do future computations, this is going to be an issue. So we need to address this, and we need to just replace it. So what we are going to do is do RGB ratio, and we're going to use a function called where, np where, and that is going to find, similar to the if statement in Excel. So we are going to first pass the condition, and then what do we want to do if it's true, and then what do we want the code to do if it's false. Okay, so we are going to do np, and we are going to check whether the items are the pixels are infinity or not. And for this, NumPy already has a really nice function. It's called isInf, similar to isNA. Remember that we use in pandas. So isInf, and then we are going to check RG ratio. So this one is the same as this one. It's just that we are going to do all the operations in this, and when we save it, when the computer is done, it's going to save it, and it's going to give the same name. So we are going to override it. That's what this means. Okay, we're going to check, and that's the condition is infinite, and there are infinity, and that is going to be either true or false, and it's going to do that for every single pixel. And then what happens if it's true? Then if it's true, we want to place, in this case, I'm going to handle this with a placeholder. So I'm going to go up here, I'm going to do placeholder inf, and I'm going to assign a value. I'm going to just give it a value of 10, and I'm going to explain now in a second why any value lower, higher than 1 should do it. Okay. We're basically ignoring, but we are replacing that with the placeholder. And then we are going to, what happens if it's false? Then we just want to keep the same value. So RG ratio. Okay, so that's what we're going to do. We're going to do the same for the blue. The problem did not happen for the excess green because there is no division here. Yeah? The problem is when we had division by 0. So when the green band is 0, that's when we have problem. Okay, let me just use BG ratio, and then here BG ratio. Okay, that should work. And in fact, at least no errors. So now we need to keep checking whether we are going on the right track. And so what we want to do is to create a histogram. So we are going to create a histogram. Again, I say that the red to green ratio is the one that does most of the classification. These other two, have little impact on the images that we typically use, like this one. So you can actually even use just the red to green ratio and will still be fairly effective. Okay, so let's actually RG red to green ratio. Let's check the size of the shape of this, and then we have 1,000 by 1,000. Okay, so if we have as an input the band that is 1000 by 1000. Now we divide that by another band that is 1000 by 1000. Then the result is another band of 1000 by 1000, which is what we have here. And let's create a histogram. So we're going to do PLT figure. And now we are going to do PLT histogram. So Matplotlib. We need to pass what is the data set that we want. So we're going to do RG ratio, and that's the value. The only problem is that this is a two-dimensional array. And for plotting the histogram, just to divide the individual values into different bins, then Python requires, or the histogram function in Matplotlib requires that we pass, a long sequence of numbers. It doesn't want to have two dimensions. It needs to be, one dimensional. So to do that, we can use the function called flatten, which basically means I grab a matrix and decompose it into a single long string, the one-dimensional array. So that's what we are going to do there. And now we are going to, let's just plot it and see what we get. So PLT show, and we get this. So you can see that we are getting maybe some, some divisions by low numbers could trigger, very large values. So we are getting something a little weird. So let's see if we can adjust this to really see what's going on behind here. So I'm going to first pass a method to define the number of beans that are being selected automatically, some sort of rule of thumb that is already in Matplotlib. I'm going to use the Scott method. There are other methods, Sturgis method, and some other rules. And I'm going to, instead of having the actual count, I'm going to have the density. So I'm going to add density true. And let's just try this now and see where we are going. And now we get a, oh, that's because I have a typo here, density. And now we got it, but we still, we have more resolution, but we still have all of these that we don't care. And again, it might just be a really high value that we don't really care. So let's see if we can, well, I say we don't really care. We don't really care because I already know that all the pixels are concentrated here, and I'm aware of why this is happening. But if you're doing this for the first time or something, part of your research, you see something like this, take your time to explore your data and make sure that you know for sure whether this is okay and you can just zoom in, or there is something to worry about, this kind of behavior. Okay. So we are going to limit the x, the limit of the x-axis, and we are going to use here 0.522. And so we are going to basically ignore all of those because there are maybe only few occurrences that actually were captured by the histogram, and the density or the frequency are very low, but still represented. Well, at least Python wants to represent that. Okay, so now we have this. And now you see a little more that some division here. And this one has a lot of green. You see that most of the area is by live canopy cover. So these are all those pixels somewhere in here. And what we found is a threshold of about 0.95 or around 1 right here divides the green part from the background pixels. Okay, so that's what we are going to do. And that's really what's going on behind the canopy app. That's one of the reasons it's so fast and it can work also in smartphones, is because it's fairly simple. It's empirical, but it's effective in many scenarios. So let's see if we can actually make this a little prettier. So I'm going to add PLT V line. I'm going to add a vertical line. And here I'm going to add the specific threshold that we use in the app. And then I'm going to do y min equals to 0 and y max equals to, let's see, we have 3 here. Let's just go a little farther, equals to 4. So basically that's the length on the y, and this is the place on the x-axis here that we are going to have. So vertical line will be on the x-axis. And then what do we want? Maybe color. I'm going to use the tomato color. And then I'm going to use a line style. And you can also use the auto-completion in case you don't remember. I'm going to use the dashed line, and I'm going to have it right there. And Okay, so that's what we have. That's the threshold that we are going to use to do the classification. But you see that this is not too bad, to be honest. But let's see if we can have a little better style. If you're if you're an R programmer, this is pretty ugly. So let's go up and let's change the theme. So we are going to use. I'm going to use the Seaborn theme, but if you want, you can just write the ggplot theme. So we're going to PLT, and this is style, and we are going to use C. I don't know if it has auto completion. Oh, Seaborn. Okay. Do that, and I will go down to. I mean, you can rerun the images. I don't think it's going to have any effect. Let's see. I think it's going to have an effect on this one. Let's run this one again. You can see that already adds some of the grid lines. If you want to get rid of the grid lines, just remove the axis as we do in this one with this, and they're gone. And so now we can rerun this. And now we got a little better, more appealing. So, okay. So this is what we are going to select. These pixels are going to be true, or they are going to represent canopy, and these other pixels will represent background. So let's see if we can actually do that computation. Let me add a few more. Okay. So let's see, quantify canopy cover. And now we are going to create that black and white image. If you're, if you ever use the Canopeo app, we display the original image with the black and white image. So we are gonna get that one. So we're gonna call it black and white. And then so here's where we need to pass some sort of rule for thresholding and to let Python know which pixels we want to consider as foreground or green and which pixel we want to consider as background. So we are going to use a set of rules, and so the rule from the actual Canopeo paper will be RG ratio. It has to be lower than 0.95, which is the same thing. That's why I place that value right here, and it has to be the blue to green ratio, also lower than 0.95. And as I said, sometimes the blue to green ratio doesn't do very much. And I'm not writing the ands. You say I'm saying them, but there is something that we need to do to handle all these statements in NumPy. So I'm going to just write them separate, and then I'm going to place them together. So this is not going to work at this point. And then the excess green has to be, usually we found, okay, empirically by inspection, that about a value of 20 is a good threshold to avoid selecting pixels that are too dark and maybe not part of the vegetation, or maybe we don't know, so it's just noise that appears there. Okay, so now what we need to do is to, we can actually do the ands like this, but that's not going to work. And the reason is because we want to do these operations element-wise. So NumPy has a special method for doing this, which is NP, and it's logical, and it had logical and, not, or, and XOR. So we're going to use the logical and I'm going to pass it. So it's RG ratio lower than 0.95, and that one, and that one, like that. Okay, so we're going to wrap up these three statements, and that should work. Okay, and let's check the shape. We should have. So it's always good to have an expectation when you're coding, so that if the computer prints the same number that you have in mind, then that means that everything is aligned. But before running, always try to have an expectation so that then you can see, why is not what I think it is, right? Why is it different? So it's always good to have an expectation. My expectation is that this is a 1000 by 1000 image. Let's see. Okay, that matched my expectation. Still, I don't know if the values are correct, but we are going to plot that, and we are going to find out when we plot the image whether that's correct or not. Okay, so now we need to compute the percentage of canopy cover. Percentage of canopy cover. And now for doing this, the only thing we had to do is to, this is going to be zeros, and let's just actually, a few values here. What do we have? See, we had trues and false. So true is where this logical statement or Boolean statement is true, and then false is when this is false. At least one of them is false. Not that we use the and condition. So that means that this one needs to be true, this one needs to be true, and this one needs to be true for the pixel in order to be quantified as true. If we want to handle options, you know, that maybe want this one to be true or this one to be true or this one, then we need to use the logical or, okay? So or and, they're logical operators. So now we need to do that. And because again, true is represented as 1 and false represented as 0, basically to get the canopy cover, we can actually just do the sum of all of this. And this is very simple. So np sum, and we are going to add all the values in here. If we do this, by default, it will try to sum, you know, column wise. But we don't want that. We want to sum all of them for. So we don't want the result for each specific column or each specific row. We want the sum for the entire matrix. And to do that, we need to flatten, again, to flatten that array. And see that this could be saved into a different variable. But we are not interested in saving these as a flattened array. We want to do this on the fly. We want Python to do the calculation, then that the result of that computation to be passed on to the sum function. We don't want to create a different variable. We could if we had a use later on, but in this case we just want to reduce the number of variables that we have, and therefore we pass it right here. So the sum of the entire array, and that we are going to divide. Now is where the size property becomes we have a problem today with shape and size. Where the size becomes handy, because now we want to divide that by the total number of elements, and we want to do that times 100 so that we compute the percentage, okay? The sum of all divided by the total number of pixels. And if we do this, we can do maybe print cover, and we have 75.72 or so. And let's go back to the image, and remember that we are doing everything for the patch here. So let's go back to our patch. And I don't know exactly what is the the right value. We got it from Python, but this looks like 70 something, maybe 80. So I think that is on the right ballpark. It's certainly not 50, certainly not 30. So that means that probably we are getting the right values. Certainly not 100. So this is sound. Okay, so we got the canopy cover, and now let's do the black and white image. So black and white image. And what are we going to do here? Very simple. PLT figure, PLT im show, and here we pass the black and white image, and then we do PLT show. Okay, we're going to do that. Now we get this. And in Canopeo, the white pixels are represent the green canopy cover. So I see this blob here of white pixels, which makes me think that is this part right here on the background. So for some reason, I suspect that Matplotlib has, something is not aligned here with the color map. So I'm going to call the C map, and I'm going to call binary, because that's what we want. And I'm going to reverse it. So instead of, so that it properly represents what we want. There you go. Okay, so now white represents the canopy. Okay, and then what else can we do here? We can remove the axis, PLT axis off, and now we have it right there. And we can do maybe PLT title, and now we can actually add the canopy cover right here, and the one that we computed, and we have it right there. And sometimes when you are dealing with this, sometimes it's better to maybe convert this value into a string. See that? See, all these green words are reserved words for Python. So print, string, those are the things that you don't want to have a variable called string equals to hello, right? Because once we do that, then we override that reserved word, and we can no longer use it in our code because it's now occupied by a different content. So let's not use the ones there. So string cannot be covered. So that could be one option. And then we have it there. We can also round it. And then maybe we just display maybe 1 decimal place. And now we have it. And then we can even pass. So what if we want to concatenate? What if we want to say percentage here? Then we can use the plus, and we can just use percentage. And we want that to put a space there. And there you go. Okay, and we can even do here at the beginning, canopy cover. We concatenate the string. Oh, what did I do wrong now? Oh, it's not comma, it's plus. There we go. Okay, there you have your first image processing. And there are more sophisticated techniques. Again, this is something very empirical. It's already maybe a little too old, but it's still you know, practical and fairly effective. So I usually enjoy teaching this to other people. But you know, there are many more sophisticated algorithms. You can use logistic regression. You can use machine learning. You can use other type of approaches to classify. And to be honest, when I started with this, the reason we went this way is because I just didn't know anything better. And so at that time, many of the tools that were available for machine learning were still a little more, you know, not very well developed for beginners. And so this is as much as I could do during grad school. So I hope that everyone does much better than I did. So now, how do we process 4 images, right? So we did all of these for one, and it looks like a lot of work. So if we want to do many of them, you may think, okay, I'm not gonna do it. I'm just gonna use some other tool. So let's see if we can actually condense all these learning into something called functions. And functions are really useful for encapsulating code and reusing the code. It has two main goals. The first one is that we define the code one time, we check it, and then we don't touch it. So every time that we have to use it, then we just call that code snippet with a name. So similar to what we do with variables, where we put some values inside of the variable, and then when we want to retrieve it, we call the variable name. The same with a function. We call the function. And actually, we've been using functions all the time here. So the summation process, the addition process of this flattened array, there is some code behind the scenes that is doing that, but we are not writing that. We already use this function or method that is already available to us. So we are going to create our own function that we can use to read all these files. So let's do that. So learning how to handle functions is actually one of the main skills, and one of the things that is going to boost your productivity, because you can write code and then save it as a function, and then every time that you want to use it, you just call it. You don't have to recode it, and sometimes you can save it. There are ways that you can save that as a your own little toolbox or library, and that you can use that in different projects. So at the beginning, when you start coding, you don't have too many of those, but as you're coding, as you're progressing, maybe first year, second year, you're going to have your own little toolbox of little code snippets that are handy for the things that you do on a daily basis. So let's do that. Define function. So functions are defined in Python with the word def, so def for definition. And now we're gonna, I'm gonna just call it canopy here because that's exactly what we're doing. And here I'm gonna pass the image. And I'm gonna keep it here. I'm gonna add a few more, but I want to show you how you should probably develop or write the code, and then how we do the polishing process of going and then refining your code, the same as we do with the figures here, right? We first place the histogram, and then we add it, or we polish it, we change the styling. So that's usually the best way to go, rather than trying to code everything at once, and then it's more prone to mistake. Of course, once you're more seasoned programmer, you can do that, but I think it's always good to go step by step. So here we need to add a colon at the end, and as soon as you press enter, it will indent. These are 4 indentations, and that has to be that way, otherwise Python will take it as an error. Okay, so we are going to do, the first thing that we want, so in this function, we are assuming that we already have the image that we are reading the image outside of the function. So the function is doing something very, very specific. We pass an image, we get the canopy cover. Okay, so maybe you are thinking, well, I also want to read the image in the function, and that will be valid. And so instead of passing the image here, you may want to pass maybe the file name, if it's like that. But in this case, I want to decouple the reading of the file from the processing of the file in two different operations. So I'm going to keep it as specific as possible. You don't want functions that do too many things. And if that is the case, you may need to split that function into more functions. Okay, let's go back to image here. So we're going to do the RGB ratio. And here, instead of defining the red band and the green band, I'm just going to keep it a little shorter. And I'm going to do image. We don't have these, right? So if we run this image, it's not going to run anything because we don't have it. So this is just a placeholder that when we pass it, when we call the function, then it will be replaced, this image, with whatever we pass on. Okay, so hopefully I will give you some, some intuition of how this works. So we define a function, but we don't run it. The code doesn't do anything. But then we need to call the function. And that's when we make use of this code. Okay, so we are in the process of encapsulating the code now. So the red to green ratio is the red band, like this, divided by the green band. So that's like this. All right. And then we have the blue to green ratio, which is image. And then we have, now we have the blue band. So all the rows and all the columns in the blue band divided by image, all the rows and all the columns, and again for the green. Yeah? So that is one way of doing it without having to define way too many variables. We're going to define the excess green. And this one was, again, let me just do image. So it was 2 times the green, which is the second band, minus the red band, minus the what's that, the blue. There you go. So now we have the excess green, and now we can actually, we can make use of this code that we have here. So I'm going to grab this, I'm going to put it here, and then I'm going to grab the canopy cover, and I'm going to place it at the bottom. Just okay, so that is what it looks like it should run. We pass the image, we do the computations, we compute the the black and white image, and then we get the canopy cover, and everything should work because I use the same words. The functions have their own workspace. So unless you invoke with some other specific words, this will be specific to the function. And then at the end, to get the result, we do return. And what do we want to return? What do we want to get when we call this code? We want to get the canopy code. Just interested in the value. Let's just assume that we are not interested in getting this for each one, which you can also return here like this. You can return more than one variable. But I'm going to just keep it simple. Okay, I'm going to run this. And it doesn't do anything because we didn't run the code. We didn't execute this. Now, Python did check that everything looks, valid Python code, but it didn't run any operations. And let's see what happens if we do something out of, see, when it's out of the indentation, it will show you that it's red, and it's going to be red, and it's going to be red, and one more, and now it's valid Python code, okay? So now we need to call it. But to call it, we need to have an image. So I'm going to use the very first image, not the patch, but the image that we did. So, well, actually, let's do the patch. Let's see if we get the same number. RGB patch. And now it should. So this RGB patch is going to be image once the function is running in the background. And we get a mistake. Operands could not be broadcast together. We shared 1000. What did I do now? RGB patch. Is RGB patch correct? RGB patch shape. Okay, 1000 by 1000. And let's see if someone can. This is the part of the day that when I start making a ton of mistakes. Oh, I think there is a problem here. See, I forgot a comma right there. And actually, so Python is going to show you that the error is on this line. And that is where the error was. Okay? So let's see if we can, we need to rerun the function so that this, is stored in the Canopia function. Now we can run it again. And now we get the right value, which is the same that we had before right here. So that means it's working fine. But we still get this, this warning. And we already know, we already handled the issue here. We can handle all this stuff, but let's actually bring it. Let's fix it as we did here. So let's add this. Let's add this here. And what are we going to do? So I'm going to define the placeholder at the beginning, and then I'm going to get this after the ratio. I'm sorry, right here. So after computing the red to green and after computing the blue to green ratio. And now that should fix some things, but we still get, we still get the same value, which is good, but we still get the warning. But because we are already addressing this, so in other words, the computer is returning that when it runs this. It doesn't know that we are handling this later on in the next step. So we are going to actually pass a little statement that will get rid of this warning, and it's going to call, we need to call it here. You know what? Actually, we can call it outside of the function because it applies to the entire notebook. So it's NumPy, it's called set error, and this one is the divide error. So we're going to ignore it. And we can also do invalid ignore. That basically will suppress, or it should suppress, that warning there. Now use this with caution because this applies to the entire notebook. And so if you are doing some other operations where you need or you want to see the warning in case just something happens, then there are other ways to handle this. And I can add that later on when I share the full-blown notebook. There is a better way to set this for a specific cell. But since we are going to be using the function in different cells, and we know that all applies to this notebook and it's fine, then we are going to use it here. But it's not the best way of using it. It's just the simplest. Okay, we have that. And now we get it. We got rid of the warning, and now we get the value. So now we can pass any image. Let's pass the original image. So what is actually, I wonder what is the canopy cover between the patch that we selected and this one? So what is the impact perhaps of the station, right? And maybe, maybe a missing row there or something. So let's see what we get with the original image that we imported. And we get 66. So there is about, what is that? A 10% difference, 9% difference. So, there's quite a bit of an impact. So now we know how to process different images. So hopefully you can see that every time that we pass something here, we are doing this. We are calling this code. So, but we don't have to write it all the time. We just write it once and call it as many times as you want. You can actually call it twice in a row. Look at this, RGB. Now, well, you can print the result, right? You can, so that we see all of them. That should work. There you go. Now you have both images, and it's also fairly fast. And so think what the computer is doing in all these, is doing the divisions of a million pixels here, and then finding which ones are infinity, and then replacing those with a placeholder, and doing these other operations. If you start thinking about all the things that are going on behind the scenes, it's quite impressive. Okay, so sometimes it looks like we are writing a little bit of code and we had to do this, but really for the number of operations that the computer is doing for us, this is really it's a really good deal for us. Okay, so now perhaps the last part of the tutorial is to learn how to read multiple of these images and then how to how to save the canopy code for each of them in case you have multiple. So, but before I move on, let's see if there is anything else that is pending here. I want to, again, emphasize the concept of defining a function and calling a function. This is sometimes called invoking a function. Yeah, defining a function and calling two different things. We can also document our functions, and Python allows us to create multiple lines of comments like this with the triple quotation marks. So 1, 2, 3, and see that another 3. And this one is for documenting the function. So we're going to do a function that computes the percentage of canopy cover. Okay, and we can even keep going below. The input is an RGB image. We just go below so you can see that. The output is the percentage of canopy, of green canopy cover again. So canopy. And then we can also add here, your name. And this was done on the 28th of April of 2021. Okay, you can actually, you can also add, updates or changes that you did in your function. Usually you don't want this to be excessively long, but something short, something descriptive. And particularly you want to give some inputs or insights about the kind of inputs and outputs of the function. Another option is that we can specify. See here, I say 0.95, 0.95, and 20, but what if we want to try something different? What if we want to test what it's going to be covered? Then we can actually set this. I'm going to set this to red, green. And now I need to replace this one here with the red, green. That will be the threshold. And in case, we don't want to pass anything and we want to call it like this, very clean, then we can assign a default value. And the default value is equal 0.95. So if we don't specify when we call the function, it's going to use this one by default. And if we specify, then it's going to change it. Okay, and we can assign. Let's just keep this one maybe. You can change these two as well and see what the impact is. But let's try. So we need to rerun it now. And now we're going to call. Let's just call the patch only. The patch like that, and then we're going to call the patch. And this one, I'm going to call it with, let's say, 0.9. And let's see what we get there. Okay, so we get a lower canopy. That means that is more aggressive on that threshold. And then we can actually set a value of, let's say, 1. And then we can see what is the impact of that. Okay, so it seems that assigning a higher value, it doesn't have a strong impact. We only increase by 4 or 5%. But if we get a really low value of the setting, then we are excluding too much canopy. Okay. So I guess the function looks pretty good. Now let's read multiple images, and we have about 15 minutes, which is I think it's exactly what it's going to take. So to read images from your file system, you will need a separate module, and I'm going to actually import the modules here because maybe some of you are not interested on that, and so maybe you want to have all these Jupyter Lab as a one thing. But technically, we will go here and we'll import the more modules that we want at the top. So if you want to do that, then go ahead. I'm just going to keep everything together in here. So we are first going to import the glob module, and then we are going to, let's just keep it like this, the glob module. Let's keep adding one at a time. So glob module, we are going to read that, and we're going to call file names. We're going to store all the file names into file names. And then we are going to call the glob, and we are going to call the submodule glob as well. And here we want to specify only images. So let's see if I can see what is the format. So we know there's a JPEG. So we want to avoid all of this. So we are going to specify, it's a string. We're going to use the asterisk. That is a wildcard. That means that it's what, regardless of the name, just give me all the image files. This is going to be JPEG. Now pay attention whether JPEG, the extension is a lowercase or uppercase. Sometimes that matters. So this is lowercase. And now let's just print this. Print file names. And what did I do wrong? Again, file names and file name. Okay, so file names. There you go. And there you have it. Okay, but there is an intruder here. It's the mosaic that I saved earlier. I'm going to delete that one so that we can. You can filter this out by slicing. You can slice from this element to the last one. I'm just going to delete it here so that you can match it. There you go. So I'm going to reread this. There you go. Okay. So we have the images. Let's move down. And sometimes this will not be ordered. See, this one was taken on 19th August 2020 at 9 a.m. This one was taken at noon, 3 p.m. and at 6 p.m. And in this case, everything appears in order. I think when I was doing the other, the final version of the tutorial, they were not appearing in order in my computer for some reason. And then I had to use the sorted function of Python. But in this case, I'm not going to use it because it already seems to be in order. And then let's just move on. Let's keep it simple. Okay, so now the idea is how do we root this? And now we need to iterate. So we have file name 1, 2, 3, and 4. So the idea is that here is the goal. We want to read each of these, compute the canopy cover, save the value, and move on into the next one. But we don't want to store the images here. We don't want to have like this, RGB1 and RGB2 and RGB3, because if we have 100, it's not going to work. We will need to do all by hand. So we want to take advantage of the, of the computer doing work for us, okay? So to do that, perhaps the feature that best represents why we use computers is called a for loop, which means that we ask the computer to iterate a specific operation as many times as we indicate. And that is actually the, using the computer to do work for us. Okay, so I'm gonna write something called a for loop. And here is when you start seeing that things start to get a little more complicated because we have logical statements, we have different modules, we have for loops, things get a little overwhelming. So this will be the last part of the tutorial. And then I will leave this up to you to find out more on your own, or just feel free to reach out to me. Okay, so for file, sorry, the for is what we want. So for is green, so that's a reserved word. So for file in file names. This word file or this variable will carry each of these names one at the time. Whenever the iteration is over, it will start another one with a different file name until they are over, okay, until they are done. So this is the list here, this one here, that has all the elements that we want. These are the elements of the list. And this one is going to have each element one at a time. So it's not going to hold a value of 0, 1, 2, and 3. It's going to hold the name. Okay, we can actually use this print file just to see. See that? So now we need to use that to our advantage. And one more advice perhaps is when you're learning, use naive examples like this one to, just again, to check your intuition, to check what the computer is doing. And once you know what it's doing, what is inside of this variable, then start building on that. But sometimes, these naive examples help you a lot just to make sure that you're moving into the right direction. Okay, so now we have the file name. So we can go up here and we can call PLT in read, but instead of having this one as a string, we are going to pass that file. So we are going to read it. So we're going to remove all of these. We're going to do PLT in read, and we are going to pass file because that's the string with the file name. And we are going to store this into RGB right here. Or let's just call it, I think just to avoid overwriting, because we already have a variable called RGB. So I'm going to call it I for image. And then what do we want to do with this image, right? We want to do the canopy cover, and we are going to do the canopy of a function, and we are going to pass that I, and that's pretty much all. We're going to print the canopy cover if you want. Canopy cover. Let's see what happens. And something is not right. What's going on? Canopy cover.
I think you need to put CC in the print.
Oh, good call. Yeah, CC. Good. Yeah, 545 is my limit for teaching Python probably. There you go. So now you see all the images. And before I keep going, let's show you, these were all taken the same day. So let's take a look at these images. Let's take a look at the one at 9 a.m., which is the one that we analyzed first. Oh, this is not looking very good. But the crop looks actually pretty healthy and the leaves are fully expanded. Let's look at the one at 3 p.m. And now you can see a substantial amount of water stress, okay? The atmospheric demand went up and the plant could not cope with the atmospheric demand. Probably the soil moisture was not the best. And so the leaves are closing. It's reducing the canopy cover. It's reducing the ability of the plant to intercept solar radiation. Probably stomates are also closed. So that means that the amount of carbon assimilation was reduced. And so the goal is to be able to put a number to that stress. And you see that then about 6 p.m., I'm gonna open that one as well, the canopy seems to be fully recovered or at least very close. And we can see that in the canopy right here, it's about 61. So it's very close to the initial 66. But look at this, there was a 23% change in only, what, 6 hours, okay? And so even here, 12% change in just 3 hours from 9 a.m. to noon. So one of the nice applications of using digital images for agronomic studies. So imagine now with the time lapse, instead of having the entire growing season, which is exactly what we actually had with this study. So we had this for the entire growing season of the soybeans. Okay, so let's see if we can do this a little nicer. So I'm going to show you how to use a structure called dictionary. So this will be the very last step. So we are going to use, I'm going to replace this CC because it's doing what we want. But let's see if we can get the timestamp from the file name. Let's see if we can have this into a pandas data frame so that then you can relate to the tutorial on day one and then use all those tools that you learned in the previous tutorial to analyze data. So let's do that. So we are going to replace CC. We are going to make it a dictionary. So dictionaries are actually really handy because we can access data by name. So we are going to initiate an empty dictionary. And we define that with curly braces. And we are going to store here the file name. And then we are going to have an empty array where we're going to store basically the same that we have here. And then we are going to store another one for the timestamp. And again, we are going to store that later on into this empty list. And we are going to have the canopy cover. So I'm going to just call this CC here. Yeah, just avoid confusion. Let's call it canopy or cover. Okay, we're going to store that into another list. This is called a key. That's the key. And this is the value. The value could be a single number like this, or it can be a list. Okay, but these are called key value pairs. And this will be one pair, a second pair, and a third pair. Okay? Key value pairs. If you're familiar with JSON objects, which is very popular for transferring data nowadays, a dictionary is very much a JSON object, very similar. So, what do we need? Now we need to fill it, right? Because we have the names, but we don't have any values in there. So we need to run the for loop and be filling the blanks as we go. So the first thing that I'm going to do, so we are going to read the image. Then we are going to do CC here. And for the file name, as you can also use the auto-completion. So for the file name, we are going to append. And then here we are going to use file because that's the file name that we have, right? So that's fairly straightforward. Now we are going to do in the CC, we are going to add the canopy cover. So I'm going to do cover here. Oh, sorry, I need to define this with a string cover. And this one will be the result of the canopeo. So this one will be here like this. There you go. Okay, so we are passing that canopy cover. And the one that we need to do a little more work now is we need to extract the timestamp from, we could extract that from the file information, but I'm gonna show you how to extract it from the file name, because many times we actually encode a lot of information in file names. So let's see if we can do that. We can do a little bit of splitting the string and using these underscores and periods to our advantage to extract these out of the way. Okay, So we're going to do that. And so let's see. We're going to first partition that. We're going to remove the extension first. So file with no extension. And then we are going to use file.split. And we are going to split it at the period right here. So that's going to separate a name that is like this and this. Let's actually do it here. We can do it in a different cell. If we do split, and then we use the period, see how you have these two. Okay. Okay. And now we are going to implement this in here. So file split, that will give us this. And now we need to select, in the next step, we need to select this part. So I'm going to do file, no extension parts. I don't know, you may want to give it a better name. And we are going to pass as file. So we're going to split it again. You're going to split it again. So file, no extension. And we are going to split this by the underscore now. Okay, so we are splitting this part by the underscore. And we need to select, so because there are two elements here, we need to do 0, right? There we go, 0. Is that correct? 0, I think that should work. And now what we want to do is create a timestamp. So we're gonna do the timestamp. And this is going to be a string because we are going to join. So now what we did is we split this one and this one and this one. The JPEG is out of the question because we only split in the second step this part. Okay. So we are going to use timestamp as a string. And now we are going to combine these two. So the second element and the third element. So that's the second element and the third element. Okay, we're gonna get that. And after that, it will be really cool once we have this. So right now what I have there is something like this. Let me show you. That's what we have right there, like this. That's what we have right here in timestamp string. That's all this sequence of operations is what we did. So it will be really nice if we can convert this into a pandas datetime and then convert all this dictionary that we are going to have here into a pandas datetime, a data frame. So let's import pandas as PD, and let's run this because again we need to have the module loaded. And now what we're going to do is to do timestamp equals pandas to datetime, and we are going to pass the timestamp string, and we need to pass the format for this. So the format of this will be year, and there is no slashes or underscore or anything or dashes, so we will be year because it's 4 digits. We have month, we have day, we have hour, we have minute, and we have seconds. And that should convert that to a pandas data. So now we have it. We need to add it to our array there. And for that, we are going to call cc timestamp at the beginning, and then equals to timestamp. See, we have the same names, but they mean different things. This one is referring to the field or the key of the dictionary. This one is referring to the datetime that we just converted. Okay, so they have the same name, but they refer to two different things. So always keep in mind that when you are accessing, pandas data frame columns or dictionary keys, you have to use it as a string. Okay, and let's actually not print this. Let's actually maybe print it here so we can see what is the end. And there you have it. So we have everything. It looks a little cumbersome. There is a library called Pretty Print that will actually make everything really nice. But we are not that interested because we are going to convert this into a pandas data frame. So df and then data frame like this, and then we can actually read the dictionary directly, and then we can do df head just to take a look, and there you have it. The file name, the timestamp in case you want to do some, plotting or something like that, or operations extracting days and hours, and then the canopy cover. And again, there is a problem, probably I missed something again. In read canopy cover, someone please help me to find the mistake. Oh, I'm getting the same value, so that means I'm doing something wrong. Let's see if I can do this again. BLT, that will be file in file name. So this should be changing, and then we are appending the file. Is this working good? Canopy cover is good, and then I'm not sure. Cover. Okay, I'm doing something wrong. I cannot see it right now, but let's see if you can find it. That would be a good challenge. And file. It seems that we are reading always the same file. No, yeah. So something. Oh no, the file names is good. So the timestamp is wrong, and the canopy cover is wrong.
You're just reporting out the last file in the loop, right?
Can you tell me? Let me see. So we are gonna do view line numbers. Okay, what line?
So when you assign the cover, you're just assigning it to the last.
Oh, really good. So I
When
need
you
to append here.
Yeah.
There we go. Perfect. Really good. So we are appending, and hopefully the same with the timestamp. There we go. That should make it work. Awesome. Perfect. Thank you. Okay, and now we are done. So now you can pass, as many images as you have in your file system, and that's a really nice way of doing it. Okay, well, maybe you have questions. Let me show you. So in case where to go next, and I'm gonna open the actual. So if you go to the end, I do have some suggestions here. Where do you go from here? There are lots of libraries that we didn't use. So scikit-image, it has a lot of functions for image processing. We have scikit-learn for machine learning and clustering. SciPy, tons of that, same as NumPy, with a lot of functionalities for time series analysis, signal processing, statistics. The stats model. So if you are, looking to do some sort of analysis of variance, which can also be done with SciPy, but this one is a little more, is a little newer and more sort of a R syntax. The grammar of how you say, X or Y as a function of X. And then X-ray, if you want to, or if you're dealing with, remote sensing images or geotiffs or netcdf files for, for massive amount of weather data for, let's say, for the entire country. Plotly, HoloViews, and Seaborn, these are also plotting libraries. Plotly and HoloViews are also interactive. Plotly is highly recommended. It's just that interactivity comes at a cost, and they had to install several additional libraries. They have a really good documentation, so I highly encourage you to go and check this out. And then the last thing is about, maybe not as good as any of these, but it's the material that I use for my Python course, which is actually a course in reproducible research and scientific computing. It's an introductory course for students with no previous knowledge of coding. And I'm gonna click here to go to the material. And here you have, a ton of examples of things that we do on a daily basis in agronomy, soil science, crop science, even some things with genetics and DNA, because several students from other departments have been taking the course. And so it takes place every spring. And if you're interested, please reach out to me, because we're in the process of changing the actual number, making this an official course. And here you can have everything from, inspiration, which I highly encourage you to go and watch this video, and then additional information on how to install packages, how, some basic concepts in reproducible research. And then we dive into data structures, simple computations. And then we dive into functions and strings and all these sort of, how to get data from the web and how to do curve fitting, So lots of examples, problems in 1 dimension, in 2 dimensions, more image analysis. This is the canopy cover that similar to what I show you today. And again, some even some symbolic math if you're interested. We don't cover everything in the course, but this is content that I've been accumulated over the years, and there is a semester project for each student. And the idea is we try to cover different things here to just to help you to solve problems and think a little different. The course is a live coding session similar to what I did in the workshop, with the difference that it's going to be in the classroom next spring, and it's actually happening also in the classroom right now. And I take the time to go through the computers and give you some feedback on why something is running or not. And there are also some puzzles and some games that we play. So the idea is to stimulate or develop critical thinking and learn how to create our own little code snippet, and not simply copy pasting a recipe kind of code snippet to do specific analysis. Is from the point of view of doing things custom made or tailor made to your research study, if you wish. Okay, well, if you are interested in this, let me know. And usually there is a maximum of about 12 students, because I really want to emphasize on providing feedback and addressing student concerns during the the class time. So there is a maximum enrollment for that class. Okay, well, I'm going to go back to Jupyter Lab, and I don't know if there is any question. We are slightly over time, but hopefully this was useful.
Thank you very much, Dr. Patrignani. And as you said, if there are any questions, please let us know so we can address those.
And I can stay here a few minutes if you have any question. Otherwise, you can just place it in the chat, and I will try to upload this again with some more detailed answers in maybe today or tomorrow morning.
Okay, while we are waiting for any question, I will take a chance to highly recommend the Dr. Patrignani's course on Python. I use all the content for my own research program, and I found it really useful, not only in terms of Python, but also for general programming. So, and you will receive high quality feedback, so you won't regret on taking that course. So if you are interested on programming, don't think twice, and go ahead and try to take the course.
Thank you, Adrian. I'm glad it was useful. And yes, as you said, it's not focused on a specific. I had to pick one language, so that's why we cover Python, and it's one of the languages that is most popular now in the job market. But it's really about concepts that will apply to any different language. Myself, I use other languages as well, but I really find the concepts with Python very useful. So. Okay, well, it seems everyone is tired. I'm tired as well. So if you have any questions, feel free to send an email to Adrian or myself, and I will be more than happy to send you some feedback or hopefully some solutions. Okay, and all of these will be available in GitHub.
Okay, if there are not any question, we will close this second day of the Apply Python programming workshop. Thank you again, Dr. Patrignani, for help and your support to this activity. And please remember that all the videos for day 1 and day 2 are available on the AGSA YouTube channel. And so hopefully you will have the second video by tomorrow morning or the afternoon, so you can watch the videos every time you want and do some rehearsal on the coding. And so with this, we'll officially end the session and we'll end the recording, Luana.
Okay, thanks everyone.
No.